3-3 in college algebra, solving some absolute value functions is what we'll start out with. Remember, absolute value means whatever's inside of here, who cares, has to come out positive, right? The absolute value of something will come out positive. They are asking us to solve some absolute value equations. We have two options. We could do it by hand with algebra, or we could go to our graphing calculator and graph each side and see where they intersect, and each one has its advantage. I feel we'll do there's only, what, 3 of these? We'll do all 3 of them both ways, well, the first 2 both ways. Remember, when you did this, you've done it a few times now, is before you can set up your 2 equations to solve, the absolute value bars must be all by themselves on one side of the equal sign. Something like this doesn't work, right? Because the bars are not by themselves. And you are not allowed to distribute through the bars. That's against math rules. You cannot distribute through absolute value bars. What you do is you divide both sides by 2, and you get the bars by themselves. So the first thing you got to check are the bars by themselves, yes or no. Then you set up 2 equations. What's in the bars should equal 9 in this case. Or take what's in the bars and set it equal to -9. And just to show you why that is again, let's pretend you can't see what's in the bars. Would you believe that if there was a 9 in there, isn't the absolute value of 9 turn out to be 9? There's something else that could be in there that makes it true, is if that was a -9 in there, correct? So that's why we took what was in the bars and we said it could either be 9 or it could be -9. And now we solve both cases. Wouldn't we say add 3 to both sides and x would equal 12? Or if I add 3 to both sides here, x would equal -6. With me on that? And wasn't that algebra pretty simple to do? That was faster than going to the graphing calculator. We put those in a solution set, by the way. But I want to show you how it's done on the graphing calculator, because it's been a while since you may or may not have grabbed an absolute value guy. So if we punch in, I'll clear all my stuff out. To get to absolute value on your graphing calculator, there's an easy way and there's a harder way. The harder way is to go math number 1. The easy way, I don't know if anybody's ever showed you this, above the 0 button, do you see where it says catalog right here? The catalog is every function that your graphing calculator can possibly do listed in alphabetical order. Well, if you hit the catalog, take a wild guess what the very first function is in alphabetical order. It's absolute value, right? So that's the fastest way to get to absolute value. I'll show you again. I hit second catalog right here. And there's the absolute value. I would type in x minus 3. And I got an older calculator than most of y'all's. Most of y'all's will actually put absolute value bars in there anymore, but mine's older. The other thing I want it to equal is 9. So you take each piece separately and make them a function of their own, and then you graph them. I'll zoom 6 it. And you'll see that I won't be able to see both of my solutions anyway. I'd have to change my window because I want to know where these things intersect at. That's when they're equal. So I'd have to totally change my window and then second calculate the intersection. But to me, that's too much work when it was so simple in the first place. So you could do it that way if you want to. I would solve this one algebraically. Number 2, I would also solve this one algebraically. It looks pretty simple. First question, though, is are the bars all by themselves, yes or no? So set up 2 equations. First one is what you see is what you get. The bars are gone, though. Right? You drop the bars, equals 8, or take what's in the bars, and it will not equal 8 this time. It will equal a -8. And then you just solve both situations. Really, really simple. So that would be 2x equals 12, x equals 6, 2x equals, add 4 to both sides, -4, x equals -2. Cool with that? And then you're supposed to go back and check them. The truth is, when it's something simple, it's linear, and there's no variables out here, right, what it's equal to, there's no x's on that side, they will work both times. Okay, I'll just tell you that straight out. You won't get any extraneous answers. You might remember that from Algebra 2 where you substitute them back in and all of a sudden this didn't work, you know. That's because there were variables over here or this was not linear in the first place or something like that. So no extraneous answers when this is not linear. What would you graph? Absolute value of this for the first function. Then you'd graph y equals 8 for the second function, and you'd see where they'd intersect. Cool? Next one. Not nearly as pretty. Why not? Squared, first power, all kinds of variables, right? So I choose to not do this one algebraically. I would choose to do this one with the graphing calculator. This stuff inside the bars is not linear. It doesn't mean you can't do it algebraically. It's factoring and all of that stuff, and I think the graphing calculator would be faster. So what do I type? Absolute value. How do I get to that again? If you just go to your catalog, which is right above your 0 key, the first option is absolute value, x squared minus 5x. And then the second thing is 6, correct? Let's see what it looks like on the standard window. That's zoom 6. Possible places of intersection. Ooh, that's messed up. It's not even the typical absolute value v, because isn't it a quadratic function inside of there in the first place? So looks like an awesome little w type thing. What I want to do, though, is I want to zoom in on this, because I don't know if there's 3 places of intersection there or 4 places of intersection there from what I see. So let's zoom in this region right here. Change my window. My window minimum can be -1. My x minimum, oh, sorry, that was, went the wrong way. I want to go -3 on x. X max of 10 was fine. But it was really that y minimum that I wanted to change. And let's see what this looks like. So I went -3 to 10 and -1 to 10. Let's see what that looks like. And now I can see a little better that how many places of intersection are there really? 4. So let's find those by hitting second, calculate. Option 5 is intersect. They ask you which curves do you want. The curves are the things that you punched in as equations. There's only 2 different equations. So the first curve, hit enter. The second curve, hit enter. Guess. I'll find that point right there at 3, 6. Ooh, ordered pair. What do we care about? What are we solving for, x or for y? We care about x, right? So I know x equals, one of them was 3. My pen would work, correct? And let's find the other ones. Second, calculate, intersect, first curve, enter, second curve, enter. Now you got to move your cursor closer to a different place of intersection. Whatever your cursor's closest to is where it'll find. Looks like x is 2 also. And then there should be 2 more. Let's find them. First curve, enter, second curve, enter. Too many buttons. -1. And then the last one. First curve, enter, second curve, enter. Way easier. Because I want to think about what it would look like if I would have done this algebraically. It's a quadratic equation inside of there. What was it at 6? Is that right? Didn't go far enough. Was it at 6? So in a solution set, it was 3, 2, -1, and 6. And it doesn't matter what order they're in, whatever order you found them in. So think about if you'd solve this. You'd say x squared minus 5x equals 6, or x squared minus 5x equals -6. You'd have 2 different quadratic equations you'd have to solve. That's why we got 4 answers, because you'd get 2 answers from the first guy and 2 answers from the second guy. That's why there was 4 different answers. So yippity-doo-dah-day. Figure out which method you like the best. It doesn't matter to me either which way you solve it. Next guy, going back to some parent functions. Plain old power functions. It's in the form y equals ax to the bth power, where a and b are real numbers and b can't equal 0, right? So the squaring function, all I want to do is sketch the parent guy. This is y equals x squared. Isn't that a parabola? Opens up. Who's the vertex of the parent parabola? 0, 0. Looks like this. This is all the stuff that I got on the wall at the front of the room. Let's do the domain of him. Who is the domain of our squaring function? Negative infinity to positive infinity. You're looking from left to right. The range went from 0, as the low as it possibly went, up to positive infinity. What I also want you to note about the end behavior of the squaring function, what kind of power is this, even or odd? That's an even power. Which way are the ends going? Same way or different ways? Same way, right? End behavior, they're both going up. If this parabola happened to get reflected over the x-axis, wouldn't the ends still be going the same way, though? They're both going down. Even-powered functions, end behavior, same direction. This is an odd-powered function, correct? That's our cubic, which looks like this. It goes this way, then this way, like the snake right there. It goes through 0, 0. Cool. And then who's the domain? Yeah, negative infinity to positive infinity. And range, how low does he go? Negative infinity. How high does he get? Positive infinity. And note the end behavior of odd functions. Are they going the same way or different ways? Different ways. Cool? Those you've seen before many times. These are like fractional powers. Is it power over root or root over power? What do you remember? Power over root or root over power? Power over root. Let's put that just to refresh our memory. Power over root. What do you think is going to happen with this odd root right here? Let's see. I don't know what x to the 2/3 power looks like. It's not something we do often enough. How can I see what he looks like? Well, I'll use Mr. Calculator. X to the 2/3 power. Clear all that stuff out of there. Type it in right. You got x raised to the, make sure you put 2/3 in parentheses. Cool. And I'll just zoom 6 him, see what he looks like. And it's really, what I'm concerned about is end behavior. You know, we'll make a rough sketch of this, but kind of looks like this. You got a piece going this way and a piece going this way, if you will. And the ends, we have two different directions of which ways they're going. What's the domain of this puppy? The domain. Negative infinity to infinity. And then the range, how low does it go? 0, inclusive. And how high will he go? Slowly but surely, it'll go up to infinity. That was an odd root. Make a note of that. My math lab questions will ask you a lot about even roots, odd roots. This is what an odd root looks like. Which way are those things going? Two different directions. Let's see what an even root looks like. Would you believe that y to the 3/2 power, if you do power over root, you've got an even root. Let's see what he looks like. Y equals, clear them out, x to the 3/2 power. And graph it. Interesting. You only have one little branch. Because what kind of root are you taking? An even root. And in this case, a square root. Right? Square root. You should know you can't take the square root of negative numbers in the real number system. If you look over at your negative x values, there's nothing over there because they can't do it. Right? You can't take the square root of negative numbers. So even roots, you only have like one little branch, if you will. One little branch. Who's the domain? How far left does it go? 0, which counts to infinity. And the range, how low does it go? 0, inclusive, up to infinity. Even roots. One little branch. Odd roots, 2 branches. Because you could take the cube root of -8. It's -2. Right, so finally, we've got these root functions where they've put the radicals in there. Y equals the square root of x. It's the same thing as this. Y equals x to the 1/2 power, right? You know, square root 1 is the power, x is the root, power over root stuff. Doesn't matter what you type in. Let's see what he looks like. Let's make a rough sketch of him. I don't know where my calculator went. There he is. Y equals the square root of x. Close that up. Graph him. Isn't that an even root? Correct? Even root. One little branch to him. Something like so. Domain, 0 to infinity, because that's how far left he goes, and it's included. Because yes, you can take the square root of 0. It's 0. And then range as so. Make me a sketch of x to the 1/3 power. Think about it first. Will it have one little branch or two little branches? What kind of root is it? An even root or an odd root? So let's see what he looks like after we graph him. X to the 1/3 power. What do you think? 2 branches or 1 branch? Should have 2 little branches. 2 little, 1 little, 2 little branches, like so, like so. Doesn't that look like the inverse of a cubic function, like it got reflected over the line y equals x, if you will? Domain, negative infinity to positive infinity. You can take the cube root of any kind of number. Positive, yes. 0, yes. Negative, yes. You will get back any kind of number also. But back here, you could not take the square root of negative numbers. That's why they weren't in the domain. Finally, the hyperbola, which they also call the reciprocal function, because it's really y equals x to the negative first, and negative exponents mean reciprocate the base. So that's why it's y equals 1 over x. If we graph it in the calculator, you get these cool little branches like so. There's our parent function. But it's got asymptotes because the domain has to be restricted. Y'all should know thou shalt not divide by 0. So what number can't x equal in this situation since he's in the denominator of the fraction? That means you've got a vertical asymptote. I want you to sketch him in also. A vertical asymptote at x equals 0. Write it off to the side. Vertical asymptote, x equals 0. There is also a horizontal asymptote at y equals 0. I'll explain that real quick, what those horizontal asymptotes are all about. It's numbers that y could never turn out to be. So for example, here's our function that we had, y equals 1 over x, and you told me we can't put 0 in for x, correct? That means I could put a positive number in there, and what's 1 divided by a positive number turn out to be every time? Doesn't it turn out to be a positive number? Isn't 1 divided by a positive a positive? If I put a negative number in for x, wouldn't 1 divided by a negative number turn out to be a negative number, correct? So y never turns out to be 0. Y can only be positive or negative and never 0. So how do you write that? The domain, if we go from left to right, we went from negative infinity, working our way to the right. Then we run into a real problem here. Where's our problem at? At 0, not included. Union, we start over at 0 to infinity. That's our domain, baby. In our range, we also have a horizontal asymptote at y equals 0. So it goes the same thing. From negative infinity is how low it goes. Comes up to 0 height-wise, but never touches it. United with 0 to infinity. All stuff you pretty much did before. Those 2/3 power, 1/3 power, you did them, but not enough of them to really remember what was going on with those even roots and odd roots. And finally, for today, direct variation and inverse variation. Direct variation looks like so. As x gets bigger, y will get bigger also. They vary directly. Right? The same thing happens. So here's what we'll do. We'll do the 4-step problem. First step that we do is we will actually kind of make up our own generic equation. It says, suppose that s varies directly as the 2/3 power of t. We need to translate him. And we got to use this format right here. The thing that is always involved with these is the k value. They do not tell us the k value. They tell us everything else. So it says S varies directly. So put a step 1 for me. This is a 4-step problem. Step 1 is to write your generic equation. S equals. It varies directly, correct? Varies directly. So you will put a k, and then it says as the 2/3 power of t, t is the other variable, and it is raised to the 2/3 power. It's just directly, the k is upstairs. Right? There's no division. Everything is all multiplication in the numerator. That's step 1. Translate this into this format. You will never know k in step 1. Okay? Step 2, substitute in stuff that they tell you. They now tell you this here in blue, that S is 64 when t is 64. So they say S is 64. K I still don't know, but t is 64, and that's being raised to the 2/3 power. Cool? Step 3, solve for k. So now in this blue equation, we have everything but k. You can do 64 to the 2/3 power if you want to. We used to do them by memory. We want to know what's the cube root of 64, and then we'd square it because it's power over root. But if you do not remember how to do that, you just type in 64 to the 2/3 power, and it'll give you that answer of 16. Reason why is because the cube root of 64 is 4, and then you take 4 and square it, and you'd get 16. So this is really step 3 now. 64 equals 16k. Notice I rearranged the order. I don't like to write k16, 16k. Now solve for k by dividing both sides by 16, k equals 4. Right? Then step 4, rewrite your original equation. Go back to the red one. S equals 4t to the 2/3 power, replacing the k value. Now you've figured out k, so this is the direct variation equation for this particular scenario. Now answer their question. Find S when t is 8. So I'm running out of space here, so I'll go over here. So S equals 4 times 8 to the 2/3 power. First of all, I rewrote it generically, then I substituted in their information. Think about it. Let's see if you can do it without punching it in. Cube root of 8. Do you know what the cube root of 8 is? 2 squared 4. So you have S equals 4 times 4. I don't care if you punch it in. I'm just trying to refresh your memory. We do have logarithms coming up where you need to know all those things, right? So 4 times 4 is how much? 16. There's the answer to the question. That was direct variation. So to do inverse, that looks like this bad boy, where you've got your x in the denominator. K is always in the numerator. All right? K, regardless if it's direct or inverse, always in the numerator. So it says here, if S varies inversely as the square root of t, let's take him and rewrite him as step 1. S varies, there's your equal sign when they say varies, inversely. That tells you that x is downstairs, or the variable that they talk about is downstairs, but the k is always upstairs. As the square root of t, so wouldn't that be written like so? Square root of t, that's downstairs. And that's it, right? So now step 2, let's sub in. It says, and S is 4 when t is 4. I did straight substitution instead of trying to figure stuff out in my head, because people are like, oh, square root of 4 is 2, whatever. Then solve for k. So 4 equals k over 2. 8 equals k. Now rewrite your original equation, substituting k back in. So S equals 8 over the square root of t. Going back to my green guy, all I did was replace k. And then step 4, let's solve this puppy. It says, what is S when t is 16? S equals 8 over the square root of 16. If you do a little mental math, I don't have a problem with that. That really says 8 over 4, correct? What's 8 over 4? 2. If you want to write 8 over 4 and then change it down to s equals 2, I'm cool with that also. Inverse, variable downstairs. K always upstairs. Okay? My math lab.